Welcome to the Explainer. Today, we're going to pull back the curtain and take a look inside the machine. We're actually going to build a computer's brain right from the ground up by demystifying one of its most critical parts, memory.
So let's just start with this question for a second. When you save a document, or download an app, or snap a photo, where does it actually go? It's not magic, right? It's all about understanding these digital spaces inside our machines, and that is exactly what we are going to unpack today.
So here's our game plan. We'll start with the absolute basics, what even is memory. Then we'll get into the big divide between the main types, look at how they're classified, meet all the different memory types you've probably heard of, and finally, see how they all talk to the processor.
Okay, let's dive right into our first section. Before we can even talk about gigabytes and RAM sticks, we really need to build a solid foundation. So what is computer memory, and what does it actually do?
And really, it's that simple. At its very heart, memory is just a place to hold all the digital stuff that makes our computers work, from the operating system that boots up, all the way to the video that you're watching this very second.
But here's the thing, memory is not just some passive storage locker. Oh no, it is an active, essential part of the whole system. It takes in data, it feeds information to the processor's brain, the ALU, or arithmetic logic unit. It takes the results back from the ALU, and then it sends those final results out to your screen or speakers. It is the central hub for all data traffic.
And every single piece of that complex information, every photo, every song, every line of code, is built from this one fundamental unit, the bit. It's just a simple on or off switch, a 1 or a 0. Everything digital, literally everything, starts right here.
And from that one single bit, we build up. You take 8 of them, you get a byte, which is about enough to store a single letter, like A. And from there, it just scales up like crazy into kilobytes, megabytes, gigabytes, and of course, the massive terabytes that we see in hard drives all the time now.
All right, so let's jump into our next section, because not all memory is created equal, not even close. The first and, honestly, the most important distinction is between two main categories that have this fundamental trade-off between speed and size.
Okay, this is so cool because it lays the whole thing out so clearly. You've got primary memory, like your RAM, which talks directly to the CPU. It's ridiculously fast, but it's pretty small and it's expensive. Then you've got secondary memory, like your hard drive. It's huge, it's cheap, but it's way, way slower because its connection to the processor isn't as direct.
Now, this core divide brings up another super important idea, volatility. Volatile memory, like RAM, is temporary. Think of it as a workspace that gets completely wiped clean every single time you shut down your computer. Non-volatile memory, on the other hand, is your permanent storage. It holds onto your files even when the power is completely off.
So beyond that big primary versus secondary split, we can actually categorize memory in a few other important ways. It's not just about speed and permanence, it's also about how we get the data out and what the memory is physically made of.
The way we actually get to our data is a huge differentiator. With random access, the CPU can just jump directly to any piece of data at once, no problem. It's kind of like finding a book in a library using its catalog number. But with sequential access, and you can think of an old cassette tape here, you have to read through all the data that comes before it to get to what you're looking for. Obviously, much, much slower.
And the physical tech matters a whole lot too. You've got semiconductor memory, which is in your RAM and CPU, and it stores data as tiny electrical charges. Then there's magnetic memory, like in old-school hard drives, which uses magnetic fields. And of course, optical memory, like a DVD or Blu-ray disc, which uses lasers to read tiny little bits on a surface. Each one has its own set of pros and cons.
Okay, so we've got the theory down, we've got the classifications, now let's meet the actual players. Let's look at the specific types of memory you'll find inside a modern computer and see exactly where they fit into this whole hierarchy that we've been building.
All right, let's break down the huge difference between these two. RAM, that's random access memory, is your computer's temporary, volatile workspace. It's where active programs run. ROM, on the other hand, read-only memory, is non-volatile, and it holds the permanent, critical instructions your computer needs just to start up, like the boot sequence. You're constantly writing to RAM, but ROM is usually set once at the factory and left alone.
And even within RAM and ROM, you've got different flavors. Static RAM, or SRAM, is insanely fast and expensive, so it's used for tiny high-speed cache memory. Dynamic RAM, or DRAM, is a little slower but much cheaper, which makes it perfect for your computer's main memory. And it's the same with ROM. Some is programmed by the manufacturer, while other types let a user program at one time. Now, flash memory. This was a total game changer. It's this special type that is both non-volatile, like a hard drive, but it also allows random access, like RAM. This unique combo, this best of both worlds thing, makes it absolutely perfect for things like USB drives, SD cards, and the solid-state drives, or SSDs, that you find in pretty much every modern computer. Okay, this right here is the secret weapon for a fast computer. The CPU is way faster than the main RAM, so cache memory acts as this little high-speed buffer. It cleverly predicts what data the CPU is going to need next and keeps it right there, super close, which saves a really time-consuming trip to the much slower RAM. This is what gives your computer that feeling of snappiness.
So if cache is the CPU's personal notepad, then registers are the thoughts inside its head. These are tiny, incredibly fast memory cells built directly into the processor itself. They hold the exact piece of data the CPU is working on at that very instant. This is it. This is the absolute fastest level of memory in the entire system.
All right, last section. Let's put it all together. We have the CPU, the brain, and we have all these different kinds of memory. So how do they actually talk to each other? How does the processor actually read data from memory and write data to it?
Let's just walk through this. So first, the CPU puts this specific memory location, think of it as a mailing address, on something called the address bus. Next, it puts the actual data it wants to store on the data bus. Then it sends a write command on a control line. The memory chip finds that exact address and boom, accepts the data. It's a perfectly timed, coordinated dance.
And the read operation is just as methodical. The CPU places the address it wants data from on the address bus. Then it sends a read signal. The memory chip finds that spot, puts the data it finds there onto the data bus, and the CPU can just grab it. And this simple little process, it happens billions of times, every single second.
So, from the humble little bit all the way up to the lightning-fast register, we've pieced together the basics of a computer's memory system. This whole complex hierarchy of speed and cost and capacity is what makes our devices work. But it leaves us with one final thought to chew on. As our demand for data and speed just continues to explode, what's next? What will the memory of the future even look like?